From an evolutionary perspective, we've evolved really big brains that are especially expensive to run. They're almost like an American Hummer. They're very, very big, they're very inefficient, and they cost a lot of energy to keep going, even at rest. And we're especially interested in physical exercise because we know that with physical activity, we can increase blood flow to the brain. There's no curative treatment for neurodegeneration, so exercise has emerged as a very, very powerful countermeasure. And the big question is, how much, what type, how often? What we're identifying there is that, especially for people that aren't in particularly great shape or they can't exercise, perform anything that's terribly exertional, a control squat, just this using gravity can be quite a useful intervention. Much of what we're doing in the lab is trying to push different aspects of exercise in terms of the type of exercise and the intensity and the duration, trying to almost hit that sweet spot where we can see maximized, optimized adaptation.
Recent advances in technology have allowed scientists to actually see how physical activity benefits the brain.
We can measure blood flow to the brain through the neck, through the head, through the skull. And what we're showing in our research is that you don't have to be huffing and puffing and doing hard exercise in order to gain targeted benefit. So the great thing about squatting is when you stand up, you're working against gravity. When you go down, you're working with gravity. And what happens is blood flow to the brain swings high and low. So the up, down, you're almost testing the shock absorbers of a car. Here you're testing the shock absorbers of the brain, and it's that swinging of flow that we think stimulates the vascular endothelium, the inner lining of the vessel, to release all of the good stuff that we need to drive some of the things like an improvement in mental ability, mental gymnastics, to cognition, memory and learning, as an example. Your ability to remember, to think, to solve problems, to ask questions. You can squat stand for 3 minutes on, 3 minutes off. If we use it as a training stimulus for up to about a month, 4 to 5 times a day, 3 to 4 times a week, we can see an improvement in the measurements that we make that tell us how quickly blood is coming into the brain when it's challenged. And actually more so than some of the standard steady state exercise interventions that would require you to exercise submaximally for say 30 to 40 minutes.
You can even throw another layer to your exercise routine to push your brain further.
As you're doing squats, you see people in the gym reading or even doing crosswords as they're exercising. So there you've got a double whammy. And what we do know is that we can further improve flow to the brain by providing what we call a cognitive stressor, a cognitive load.
Oxygen deprivation experienced in some extreme sports can also be used as a stressor to push the brain's limits and to understand how its defence mechanisms work. As a former athlete himself, Dr. Damien Bailey is a subject in his own research.
You've got to practice what you preach. We'd use a whole range of extreme sports where we can challenge the brain in order to gain different insight into these mechanisms. Things like free diving, a single breath, no oxygen. Skydiving, stress and less oxygen. High altitude mountaineering, lots of activity, less oxygen. We're so sensitive to oxygen lack. So when we go, for example, to high altitude, to extreme altitudes, extremely low levels of oxygen, we get this increase in flow. So the brain is compensating all of the time. It's a bit like a tightrope walker. You're walking across this, what we call bioenergetic tightrope. You've got to make those necessary adjustments in order to stay on the tightrope. These models are, great ways of poking the brain to see how it responds.
Tracking these brain's responses might shed light not only on how to treat illnesses like dementia, but also on how to make long-term space missions possible.
The brain is especially sensitive to changes in gravity. You can take gravity away completely in space, right? And what happens is blood flows up to the head, and you've only got to look at astronauts' puffy faces, red puffy swollen faces, and skinny legs. And one of the potential complications with that is that over the long term, this can potentially raise pressure inside the brain, and that can influence your vision. And this is a big problem. In fact, this is one of the biggest problems that we're battling with and looking to do experiments to try to understand and to solve and develop countermeasures for a man/woman flight to Mars.
Italian researchers have developed a model with mice to investigate this topic.
We thought, but what happened when you cannot move? Because there are situations such as now where people is on the couch for many months because there is the restriction due to COVID, or because they are sick, or they have to stay on the space for many months.
The mice's hind legs were suspended, but the front legs were left free. This meant that although the animals were unable to move, they could still feed themselves.
After 14 days of the unloading, we found that the neurogenesis of this model is decreased.
In fact, they found a staggering 70% decrease in the number of neural stem cells compared to a control group.
We always think about circulation, about bones, of the astronaut, but we have to think also about the brain performance.
Inactivity reduces blood flow to the brain, and not getting enough oxygen can have dire consequences.
When things go wrong with the brain, you only need a very small window in order to induce damage. So that's why we're interested in physical activity. It's the only countermeasure out there at the moment, and we're just starting to scratch the surface as far as the brain is concerned.